Hello, everyone. In this video, we are going to continue our work on section 2.9 on applied optimization. We are now looking at number 4. So if you hadn't had a chance to read this question and try to work out the solution on your own, please do so before continuing to watch. But now let's look at it together. So a concert promoter has found that if she sells tickets for $50 each, then she will sell 1,200 tickets. But for each $5 she raises the price, 50 less people will attend. So the question is, what price should she sell the tickets at to maximize her revenue? So for this optimization problem, we want to find the maximum of a revenue function. So we need to find the revenue function. So just to recall, revenue, that's the amount of money we're bringing in. So revenue is equal to price times quantity. So in this problem, we need to find both the price and the quantity. What we are given is some information about how the price of tickets relate to the quantity or relate to how much she can sell them for. So we're given this linear relationship between price and number of tickets. And we see that it's linear because we're told that if she reduces the price $5, so for every $5 she raises the price rather, then there's a consequence on how many tickets she's going to sell. So for each chunk of $5 she raises it, there'll be a chunk of 50 less people that will attend. So we can set up a relationship here between, or we can rather understand this relationship between price and number sold as a linear function. So we can consider price and quantity sold, so P and Q. So if the price is $50, quantity is 1,200. If the price is $5 more, so 55, then how many people will she expect to attend? Well, 50 less than 1,200. So that would be 1,200 minus 50 or 1,150. So, and this relationship would continue. If she raised it to $60, then there'd be 50 less people, so 1,100, etc. So we see that this is forming a linear relationship. So we can then determine how many quantity she's going to have in terms of the price, M times Q, or M times P plus B. So this is just writing that equation of a line, but I'm just using X's for P's and Q's for Y's. So it doesn't matter what variable or letter I'm using to represent the variable. I'm using P's and Q's here just because in our situation, we are dealing with P's and Q's, prices and quantities. So let's find that equation. Q equals MP plus B. So we first need to find the slope, M. So that would be the difference of our outputs divided by difference of our inputs. So we'd have 1,200. M is equal to 1,200 minus 1,150 all over 50 minus 55. So for us, that would be 50 over -5, which is equal to -10. So our slope is -10. So setting up our equation, we have Q equals -10P plus B. So now we can plug in one of our points into P and Q in order to find B. So I'll just plug in this first point here. So I have 1,200 is equal to -10 times 50 plus B. So just computing that out, -10 times 50, that's going to be -500 plus B. So I add 500 to both sides, and I get B is equal to 1,700. So I have my slope, I have my B. So now I have this relationship between P and Q. So I'm going to fill in there. I have -10 times P plus 1,700. So there's our relationship relating P and Q. So then the revenue then I could write as follows. Revenue is equal to P times Q. But this revenue function is a function of both P and Q. But oh, hey, I know how to write Q just in terms of P. So I'm going to substitute that into my revenue function. So revenue, just as a function of P, will look like price times -10 times P plus 1,700. So now I'm going to multiply that P into both terms. So revenue as a function of P is equal to -10 P squared plus 1,700 P. Lovely. So now we have our function revenue in one variable, just P. And so we want to know how to maximize that revenue function. So what do we do to find the maximum of a function? We need to find its derivative. So we need to find our prime of P. So we can just use the power rule here. We get -20P plus 1,700. So we need to find the critical values of our derivative here. So is our prime of P ever undefined? Nope, just a nice polynomial or linear function here. What about where our prime of P is equal to 0? So for that, we need to determine where 0 is equal to -20P plus 1,700. So to do that, I could add 20P to both sides. And I get 20P equals 1,700. So dividing both sides by 20, I get that P is equal to, well, I got to compute 1,700 divided by 20. So we can do that on our calculator. If I can find my app here. There we go. 1,700 divided by 20. We get 85. So here, this implies P is equal to 85. And now let's just check that for that P, that is in fact a maximum of our function. So to do that, I'm going to test the second derivative. So I'm going to find our double prime of P. Oops, that's not the derivative that I want to take. I'm going to take the derivative of this guy over here. So that'll just give me with -20. So no matter what P I get, the output, or what P I put in here, the output is going to be -20. So even our double prime of 85 is going to be -20, which means that my second derivative is negative, which means my function is concave down. So at that point, 85, I do have a max. So then we can summarize our solution here. So we can say that she will maximize revenue if she sells the tickets for $85 each. And I encourage you right now as well to just pause a little bit and reflect on what we just did and the solution. So it's really cool that if we know a relationship between how many tickets we're going to sell and the price we're going to sell them at, then just by computing that revenue function, we can find what price our revenue is actually going to be maximized. And we can see this should make sense that we have a maximum, because if our price is larger and larger, well, fewer and fewer people are going to buy them. So it might reach a place where, diminishing returns. It's not worth selling the tickets for that price because fewer people will actually attend. But if we sell them for too cheap, a lot of people will attend, but our prices will just be so low, we're not going to get enough money. So it's super cool that our revenue function in this case does have a max, and we're actually able to determine exactly what that maximum or what that price is to give us a maximum return. All right. Thanks for watching, everyone. Great work.